Okay. So the formula unit is the most basic ratio of the ions in the crystal, and the empirical formula is the chemical formula of that formula unit. Make sense? And you just multiply it billions upon billions of times, and you got crystal. It's all crystal. Okay, if this makes sense to you, give me a thumbs up. Okay. If you have a question about it, raise your hand and wave it around. Put your hand in the air and wave it like you just don't care about school. All right, so we talked about metallic bonding in the last unit. Question? You want me to go back so you can take a picture of it? Okay. So we talked about metallic bonding in the last unit, and all the cool things that metallic bonding gives us. So I just want to talk about it again here. So again, the word we use is delocalized, meaning this nucleus doesn't know where its electrons are. It's sharing them throughout all the electrons the electrons see. It's an extremely strong bond, and it gives metals all their really cool properties. Oop, I got it. Sorry, I got it. There you go. So again, you learned about luster back in August. What is luster? Shininess. You learned about malleability. What's malleability?
Able to be formed.
Able to be pounded into sheets and hold that shape. Like they pounded the aluminum rods in the tripod into a shape, and it stays that way. Into a sheep. Ductility, good thing we have ductile wires, and then electricity conducts heat. And that's all due to the electron C model. Okay. Give me a thumbs up if this makes sense to you. Okay, wave your hand around if you need to talk about it some more. All right. Okay, so covalent bonding. One of the other words you use for covalent bonding is molecular bonding, because a molecule is formed when things covalently bond. So in a covalent bond, atoms share, just like our sulfur and our oxygen. Sulfur says, I'll give you two, and oxygen says, I'll give you two. Okay, let's share. So they share. That's covalent bonding. And it's an extremely strong bond, and the molecules want to get really close together, but not too close, because if they get too close, what's going to happen?
Because then they're going to share electron bonds that are going to merge.
Yeah, the electron clouds will repel. If they get too close, the electron clouds will repel. So this guy's electrons are attracted to this guy's nucleus, and this guy's nucleus attracted to this guy. They like get close together, but not too close. Now, covalent bonding happens only between two nonmetals. Covalent bonding happens only between two nonmetals. Where do you find the nonmetals? Everybody point to the nonmetals. Right there. It's a triangle on the side of the periodic table. It's this triangle right up in there. So right here, these are our nonmetals. Just these guys. So boron, carbon, phosphorus, selenium, iodine, bromine, chlorine, sulfur, fluorine, oxygen, nitrogen, and of course hydrogen over here because
what the heck? Oh, you what the heck are we going to do?
I know hydrogen. You could put it right here if you wanted to, but it's over there. It's right there. It's all anyway. And sometimes the metalloids can also bond covalently too. Like, remember, diatomic molecules. The diatomic molecules are all formed from covalently bonded atoms. Bromine needs one. This bromine needs one. So this bromine says, hey, can I have an electron? And this bromine says, yeah, you can have one if I can have one of yours. Br2. Okay? Iodine shares one. Chlorine shares one. Hydrogen shares one. Fluorine shares one. Oxygen shares, guess how many? 2. And nitrogen shares, think about how many nitrogen would share. Find nitrogen on the periodic table, hanging out between carbon and oxygen.
Right there, 14. Oh.
So how many would nitrogen share with another nitrogen? 3. Nitrogen shares 3 and 3, making it a triple bond, which is very strong. Nitrogen is what we use if we're going to do welding, but we don't want it to explode. We don't want any oxygen in there. We use nitrogen in there because nitrogen is considered to be an inert gas. Inert gas. When I was at Oregon State, we did some reactions that would react with oxygen, so we couldn't do them under oxygen. Otherwise, the reaction wouldn't work. So we did it in a box, kind of like a fume hood, but it was sealed. It was airtight. And you basically do your reaction, you get your gloves, and you do the reaction, and it basically, all the air goes out, and it's filled with pure nitrogen. So you can do your reaction. That way, there's no oxygen in there, because it's inert. It doesn't like to react. It's highly unusual when nitrogen reacts. Okay, questions? Thumbs up if you're good to move on. Wave your hand around if you want to talk about it some more. Cool, all right. All right, bond length. I need some volunteers.
I'll do it.
Of course you will. There you go.
Oh.
Andrew, hit that back. Anyone else have volunteer?
Actually, I don't.
Okay. Oh, at your feet. Let's see if I can get this one all the way back to Jagger. Whoa, look at that. It went up over your head. It's in the back. So this is what I want you guys to do. You have rubber bands? I want you to take the rubber band and then stretch it, like right before the breaking point. Just like this. Stretch it.
Oh, right before the.
Like your fingers and stretch like this. Okay, so you can all see. Jaggers in the back and the Rose twins. There you go. Okay, so this would represent a single bond. Each stretch of rubber would be one electron. How many electrons do you have to have a covalent bond? You have to have 2. Each atom has to donate 1. So one of Cannon's fingers is 1 atom. The other of Cannon's fingers is another atom, and they're each sharing 1 electron. Make sense? Now double it. Twist it in the middle and double it.
Twist it in the middle like this? Oh my
no.
God.
Take it and double it so there's 2 pieces of rubber. There you go. So Jagger's got it. So Jagger's left forefinger is 1 atom. Jagger's right forefinger is another atom. And how many pieces of rubber go across?
4.
4. So 4 electrons are shared in a double bond. Make sense? So what do you notice about the double bond?
That is smaller.
It's smaller, and it takes a little bit more oomph to go. So a double bond is smaller and stronger. And Jagger's already got to the triple bond, so possibly it might be an octal bond, but there are no octal bonds. A triple bond, you double it twice, or you double it and then flip it over again. A triple bond would have how many electrons?
Oh my God, it's gonna break that. 6.
6. A triple bond would have 6 electrons, and it would be shorter still and stronger still.
Quadruple, you ready?
There are no quadruple bonds that we know of. Okay? So a triple bond is stronger than double bond, is stronger than a single bond, and all atoms, this is the graph, all atoms will attempt to get to a distance that balances the attraction of this guy's nucleus for this guy's electron cloud, and this guy's nucleus for this guy's electron cloud. They balance. Okay? Now, if they're too far away, then this guy's nucleus doesn't really see this guy's electron cloud, and they are very high in energy. So this is a scenario where they're very high in energy. As they get closer, they get lower and lower and lower in energy until they're just right. But if they get too close, then they start pushing away from each other. Does that make sense? Here's another example. This balloon and this balloon, if this balloon is attracted to this balloon, they get to a certain distance right about there. Now, if I push them together, they start pushing back really hard.
Yeah.
To the point where they actually might just pop up.
I'm scared.
Okay? So here, this is a high energy scenario. They don't like that. Lower, 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 lower. Pretty good. Then when they get closer together, not so good anymore. Okay? So atoms want to attain a low energy environment. Just like you and I. That was my only rubber band.
Yeah, can you take the rubber bands?
Ew. Shut up.
Okay. Okay, yeah. Up here. Cool. All right. So, yeah, good luck with that. Anyway, so does that make sense?
Yeah.
atoms arrange themselves so their molecule has a very, very low energy state. It wants to have as low potential energy as possible. So when they get to just the right distance, this balances out the attraction of one atom's nucleus for another atom's electron cloud, and this atom's nucleus for this atom's electron cloud. Okay, does this idea make sense?
Yes.
Okay, give me a thumbs up if you're ready to move on. Wave your hand around if you want to talk about it some more. All right. Okay, so remember, electronegativity is the phenomenon that says this is how strong an atom is going to pull electrons from another atom. If you have two covalently bonded atoms, but one of them has a higher electronegativity, the electrons will spend more time around the more electronegative atom. I'll say it again. If you have two atoms that are bonded covalently, but they're not alike, the electrons will spend more time around the more electronegative atom. So, look at sulfur and oxygen. Which one's more electronegative?
Sulfur.
Oxygen. So, in the bond is going to spend more time around oxygen than it is around sulfur. Does that make sense? Okay. Similarly, here's another one. Carbon. So oxygen and carbon. Which one's more electronegative, oxygen or carbon? Oxygen. So where's that electron cloud from the bond? Going to spend most of its time around oxygen. So the bond cloud would look something like this. Make sense?
Yes.
This creates a polar bond. Guys, I know you can do this, and you can do this. So, which side is polar in the sulfur-oxygen bond? The left side or the right side?
The left side.
If you think it's the left side, raise your hand. If you think it's the sulfur side, raise your hand. If you think it's the oxygen side, raise your hand. It's the oxygen side. So this is going to be the partial negative side, and this is going to be the partial positive side. Now with the carbon-oxygen, do you think it's going to be the oxygen is going to be negative or the carbon's going to be negative? The oxygen. Hopefully you can see that this is going to be the partial negative side, and this is going to be the partial positive side. By the way, to make the partial symbol, this is a lowercase delta. You just make an S, a little loop on the end. Greek letters, yeah. So a polar covalent bond will have a dipole. I know all these words. I don't like learning just to be words.
Stop.
Yes. So you have, I wish you guys could appreciate just how good your chemistry teacher is. Most chemistry teachers like reading the book. What is a dipole? What does a dipole mean?
Means that it's both electron or negative and positive, so it has both.
Di means two, and poles are like North Pole, South Pole. A dipole is two poles, and this is how you draw it. Are you ready?
Yeah.
You make an arrow. You make an arrow with a positive on one end pointing to the negative. This is a dipole. Dipole. There's a pole and there's a pole. So you make an arrow. A dipole is an arrow with a positive on one end that points to where the negative electrons are. Which direction is this dipole going to go? Show me with your hand. Where's this dipole going to go? Yeah, most of you realize it's going to go this way because the partial positive. That should be a positive sign over there. The partial positive is on the carbon, and the oxygen has a partial negative. That's a dipole. Make sense? All right. Now, what if you have two atoms sharing electrons? Like, I don't have two oxygens. Let's pretend I did. What if you had an oxygen and another oxygen, and they shared electrons, like an O2, like you're breathing right now? What kind of bond would that be?
That would be a I guess, non-metallic bond.
It's non-metallic, but it's also
Polar.
it's non-polar. Yeah, if you have two bonds, or if you have two atoms that are identical or have the same electronegativity, we call this a non-polar covalent bond. This idea about polarity is where we're going to spend pretty much all of our time in this unit. Is it polar? Is it not polar? Okay. Questions? We're almost done. We have one more concept to talk about. Has anyone ever done vector addition in mathematics? You have. Yes, you have. So if you take an arrow that looks like that, and you add it to an arrow that looks like that, what's the result? Yeah, a longer arrow that looks like that, right? And remember number lines?
Oh, yeah.
It's like, oh yeah, number lines, I love those. I wish math could just stop at number lines in 3rd grade. So now you can do this in 2 dimensions too. If you take an arrow that looks like that, and you add it to an arrow that looks like that, what's the result? An arrow that goes up like that. Well, it turns out dipoles work exactly the same way.
No.
To find out if a molecule is polar, this is where we're going to end. To find out if a molecule is polar, you simply add the bond dipoles together. So this is water. This is also water. This is upside down. There the hydrogens are pointing down. Here the hydrogens are pointing up. If I was to draw the bond dipoles on my water molecule, what direction would this hydrogen-oxygen bond dipole point? See if you can point with your finger. Where's it going to go? Yeah, most of you realize it's going to go down. So this has a bond dipole that points like that. And this one also has a bond dipole that points like that. We tend to draw the dipoles parallel to the bond whenever possible. Make sense?
Yeah.
Okay, because they're vectors, and you'll learn what vectors are when we take physics. So then this one plus this one, what direction would the molecular dipole point? Most of you realize it would point straight down. So water is a polar molecule because the oxygen-hydrogen bonds are polar. Okay, last chance. You got 90 seconds. Any questions? All right. Press the button.